everybody, and welcome to Unit 4, Lesson 3. Now, this is going to be a continuation of our previous discussion about straight line motion. So our learning target is the same. So we're going to be using derivatives to solve rectilinear motion problems, and we're going to be looking at position, speed, velocity, and acceleration. Now, what we're going to be doing today, which is a little different, is that we're going to be analyzing the graph of a velocity function. Now, this is important because I want to make sure that we realize we are always going to be looking at the graph of velocity. So what we talk about today, is going to be very similar to what we've discussed in the past, and the thinking methods are going to be very similar to what we've discussed in the past when we looked at the graph of f prime. And we said, where is the original function increasing is where this graph is above, decreasing is where this graph is below, that kind of thing. The only difference is that now, because this is a straight line motion problem, instead of calling this f prime, we're going to call it velocity. So you'll notice a lot of the thinking processes are the same. So it says here, we are often asked to analyze the motion of a particle using a given graph of the velocity of the particle. The graph below shows the velocity of the particle moving along an x-axis. So we have an object that's going back and forth along the x-axis. This is telling us the velocity, or how fast, and the direction that it's going at any given time. If I want to know a velocity value, so if I want to know, for example, find the velocity of the particle at t equals 14. To find the value of velocity, you just look at the y values of the function, because this is the velocity graph. So if I want to know the velocity of the particle at t equals 14, I'm just going to look when t is 14, what is that y value? That y value is 3, so the velocity would be 3 feet per second. In this case, it's feet per second, and time is in seconds. Now, moving to the right is when we want to look for where the velocity is positive. The velocity is going to be positive when this graph is above the x-axis. So think about this as being very similar to when I used to ask you, where is the original function increasing? Having a positive velocity means that we want to know when the velocity is above the x-axis. So when is the particle moving to the right? It's going to be whenever this graph is above the x-axis. So it's going to be from 0 to 3, and then 9 all the way over to 19. So we would say from 0 to 3, and then also from 9 to 19. If we want to know when our object is moving to the left, we're going to be looking for where the velocity is negative, which is going to be where this graph is below the x-axis. So the object is going to be moving left in all of these sections of the graph here, where we're below the x-axis. So my answer would be from 3 to 9, and then also from 19 to 20. If we want to know when our object is stopped, we want to know when the velocity is 0. So these are going to be the x-intercepts of this graph. So when is the object stopped? I would say it's going to be stopped at exactly 3, exactly 9, and exactly 19. Next, we're going to be talking about other things that we can find that are not just kind of looking at positive, negative, and 0 values for velocity. The next question is speed. The speed of a particle is the absolute value of the velocity. So it's taking the rates, but it's making it always be positive. For example, if I say find the speed of the particle at t equals 8, I'm going to start by finding the velocity at t equals 8. So that means on this graph, I'm going to look when t is 8, what is the velocity? And the velocity would be -1. So I'm going to do the absolute value of -1, which would just be 1 foot per second. So my speed would be 1, even though my velocity would be -1, because speed is just the absolute value of velocity. The acceleration is going to be the derivative of my velocity. Since I'm finding the derivative, I'm going to be looking at the slope of this graph. You can think about this as kind of like finding the second derivative, or talking about concavity. So if I say find the acceleration of the particle at t equals 8, I need to know the slope of this graph at t=8. So I'm going to find the slope of this line. Now that line, if I look at rise over run, we go up 3 and then we go right 3. So my acceleration would be 3 divided by 3, which is just 1 feet per second squared, because it's now the second derivative, so it's the acceleration is feet per second, or feet per second squared. Now, speed is going to be increasing when your velocity, your y values, and your acceleration, your slopes, have the same signs. So either the velocity and the acceleration are both positive, greater than 0, or the velocity and the acceleration are both negative, which is less than 0. On this graph, that means velocity is greater than 0 means above the x-axis. So it's the parts that I already highlighted in orange. And acceleration being positive or greater than 0 means that it has a positive slope. So if I look at this graph, I'm going to look at the orange parts, the above, and look for the ones that also have a positive slope. And that's going to be here from 9 to 12. So I'm going to say that my answer here would be from 9 to 12. Now I'm going to use open parentheses here because anytime we deal with the second derivative or acceleration, we always use open parentheses. Now the second option here is that both of these values could be negative, it's still going to make my speed increasing. So if my velocity is negative, it means I'm looking at the parts of the graph that are below, and then acceleration being negative means I'm looking for where those parts of the graph have a negative slope. So where am I below and also have a negative slope? And that's going to be right here as well as right here. So there's going to be two parts. So I'm going to say from 3 to 4 and also from 19 to 20. Oop, I just realized you couldn't see that. Last but not least, speed decreasing. So this is going to be when your velocity and your acceleration have opposite signs. So my velocity is going to be positive. I'm looking above the x-axis, but I'm looking for where acceleration is negative. So I'm looking for above and downhill. This part of the graph is going to be, if we look for above and downhill, it's going to be this part right here, and also this part right here, and also this part right here. So that's going to be from 0 to 3, and also from 15 to 17, and also from 18 to 19. Last but not least, if I want to know the other option for slowing down or speed decreasing, it's when you have a negative velocity but a positive acceleration. So you're looking for where you're below the x-axis but you're uphill. It's kind of opposites. So if I look for below the x-axis but uphill, it would be this portion of the graph, which goes from 6 to 9. Okay. Here is an example of a type of FRQ and some questions you might see on a test or an AP test. It says the accompanying figure shows the velocity of the particle moving along the x-axis. So we've got a velocity function. If I look at this graph, I notice that the y-axis is counting by 20s, and the velocity is meters per minute, and the time is in minutes. And I notice that the x-axis is counting by 5. So it's like 5, 10, 15, 20, 25, 30, 35, 40. That's going to be important when I'm listing my values. If I want to know when the particle is moving to the right, I'm looking for where this graph is above the x-axis. So that's going to be this portion of the graph right here. I'm moving to the right because my velocity is positive, or in other words, this graph is above the x-axis. So I would say from 0 to 30. And I would say my reason is because v of t is greater than or equal to 0. If I want to know when this particle is moving to the left, then I'm going to be talking about below the x-axis, which is from 30 to 55. So I would say from 30 to 55 because my velocity is less than or equal to 0. When is the particle stopped? So stopped is going to be when the velocity is exactly 0. In this case, that's going to be right here. right here, and right here. So x-intercepts. So I would say at t equals 0, 30, and 55, because those are the places where my velocity is exactly equal to 0. Those are the x-intercepts. Next, it says, what is the speed of the particle at t equals 35? So speed is going to be the absolute value of that velocity. If I look on the graph, when t is 35, the velocity is negative 20. So the absolute value of negative 20 would just be positive 20, and that would be meters per minute. When is the speed of the particle increasing? So I'm going to look for two different situations. Either both velocity and acceleration are positive, so above and uphill, or velocity and acceleration are negative, so below and downhill. So I'm just going to make a note of that. This is going to be above and uphill, or below and downhill. On this graph, that's going to be right here, above and uphill, or below and downhill would be right here. So I'm going to say that the speed is increasing from 0 to 10 and also from 30 to 40 because v of t and a of t, velocity and acceleration, have the same signs. So they both are positive or they both are negative. And last but not least, when is the speed of the particle decreasing? So speed is going to be decreasing whenever we are above and downhill. I'm going to use blue for this. So it's going to be above and downhill. So kind of like opposites, right? Above but downhill, or below and uphill. So in this case, it would be from here to here and from here to here. So I would say that my answer is from 15 to 30 and also from 40 to 55. There we go. And I would say because v of t and a of t have opposite signs. So one of them is positive and one of them is negative. All right, that is it for today. Thank you all so much for watching, and I'll see you soon for some practice.